Good afternoon. I'm Haodi from Zhejiang University. Today I'm honored and excited to present my work, here, where ME means multi-effective receptive field, and our proposed method is for scale-variant object detection in scenarios of underwater optical sensing. So let's step into the details. Here's an overview of my presentation. I will start with the background and challenges. Then I will introduce the motivation. Then we'll look at the method and results. Underwater object detection presents several unique challenges that significantly impact model performance. First, underwater objects have complex features that are either shape biased, requiring attention to global structure, or texture biased, where fine-grained local details are crucial. Underwater images are often degraded due to refraction, scattering, and uneven lighting, which lead to low contrast and blurred edges. And underwater object exhibits variations in sizes and scales. So, for example, objects at close range require the model to extract features of long-range context, while objects at a distance require the model to focus on local details. And it is often a trade-off in vision tasks, especially for data-driven tasks. Here I want to show how we think about these problems and how we try to solve them. First, I would like to distinguish the concept of the receptive field. So when referring to the receptive field of model, we often mean the theoretical receptive field. It refers to how much of the input image a neuron in a layer can perceive. In this example, we perform two convolutions in the layer 1 using a 3x3 convolution kernel, where the green pixel in layer 2 is computed for 9 pixels in layer 1. But however, NIPS introduced the concept of effective receptive field, indicating that not all pixels involved in the computation contribute equally. Pixels in the center of the receptive field have a greater impact on the output, and the effective receptive field often follows the Gaussian distribution from the center. This is the main idea we want to show in this work, and find what the model can actually see through the whole area. So another inspiration comes from an architecture that maintains high resolution throughout the process. MENet follows the idea of high resolution representation inspired by HRNet. Maintaining spatial details throughout the network, our model also benefits from high resolution throughout forward propagation and multi-scale interactions at the gradient level, which leads to a high sensitivity to global context. After considering the resolution problem, we need to look back on the most challenging part, is that how to handle the ERF problem well. So this is a one-dimensional formulation to describe the ERF. And similarly, for 2D convolutional images, we can derive its two-dimensional formulation. It is indicated that the ERF of a 2D vision model is linearly correlated with the kernel size. So this is the way we enhance the ERF in today's model design. Performance of large kernels have been rediscovered in recent years using model kernel design techniques. We can even scale up the kernel size to 31 by 31. And the green area indicates how many of them actually influence the prediction. ResNet can have layers up to 152, but the ERF is not that large by the increase of the layer numbers, while 50 layers of large kernel can have a satisfactory wide ERF. So, however, it is a trade-off between large and small kernels. Networks with small kernels miss long-range context in the large object detection, whereas those with large kernels introduce noise from small parts. So, addressing this trade-off is what I want the model designed to achieve. Here we see the methods. Traditional models often rely on fixed kernel sizes, such as 3x3 kernels, which can limit their ability to adapt to varying resolutions. So our method employs size-adaptive kernels that dynamically adjust to match the resolution of the feature map. This ensures that higher resolutions benefit from larger kernels, capturing more global context, while lower resolutions use smaller kernels to retain local details. This design eases the trade-off between large and small kernels, which is also between redundant background noise and long-range context. And this is part of our approach to addressing the scale variant problem in underwater scenes. And here I want to introduce the EF server, a key component in our architecture. And it is designed to actively regulate the effective receptive field within the network and to better adapt to varying object scales to ease noise in underwater environments. This model introduced two additional streams known as userve and dserve, which operates on different channels to achieve balance between global and local, where the first one enhances the ERF by stacking larger upper bound kernels, allowing the network to capture long-range context, which is essential for long and large objects at short distances. On the other hand, dserve limits the ERF using 3x3 residual small kernel propagation, preserving finer local details and preventing excessive smoothing caused by larger kernels. So to briefly summarize, two additional information streams, global content and local details, are well preserved in later processing. We will utilize this information for fusion. And this is how we fuse these features using a parallel fusion with skip connections. It is a crucial part of our network's texture that enables the integration of multi-scale information. We supplement the information from early downsampling stage to later upsampling stage and fuse these three information streams. The current resolution matched semantic information, global large receptive field information, and global small receptive field information are fused at the output to jointly predict. By using skip connections, the network ensures that information flows smoothly across layers, preserving both high-level context and fine-grained details. This parallel fusion approaches makes it particularly robust for challenging underwater detection tasks. And here we check the results. We compare the performance of different kernel sizes across datasets, and the proposals to evaluate how different kernel sizes impact the detection performance, particularly for underwater images with varying object scales, as shown in the table. The classic 3x3 kernels provide decent performance, but struggle to capture long-range context effectively. Larger kernels, such as 2727, improve performance by capturing more global features, but they introduce noise and lose fine details for small objects. So MENet against other state-of-the-art work, we tested on our model on two widely used underwater datasets, UFO 120 and MES3K, as presented in the table. MENet achieves the highest MIOU, which means intersection over union on both datasets. The comparison images on the left demonstrate that MENet consistently delivers more accurate object boundaries and segmentation results compared to previous methods, effectively handling the noise and variations in object size. And here we make a short summary. Our research tackles challenges, especially scale variations of objects at different ranges in underwater scenarios. Our approach integrates resolution matching kernel sizes to align kernel dimensions with feature resolution. Employs the ERF server to actively regulate receptive field growth and control noise, and utilizes parallel fusion with skip connection to ensure smooth interaction between multi-resolution features. Together, these models enables a wider and more refined ERF range with resolution interaction. Additionally, when submitting this paper earlier this year, we discovered that similar model design has also emerged in conferences of other fields like remote sensing and medical imaging. The difference is that our research is inspired by underwater sensing environments. So if you are interested in this topic, feel free to follow the latest research developments. I also work on discussions with you. Thank you for listening.